Hello, welcome to the Gen Chem series, and today we're going to be doing something a little different. So this is going to be our first concept review video. So what it is I've gone ahead and made a 19 question worksheet that you can download in the description of this video. You can download it as like a PDF file. And the 19 questions are going to be reviewing the content in the past 5 videos. And the other kind of thing that's important to know is I've made these questions to be in the style of the MCAT, which means that like kind of the wording of the questions and the formatting is going to look very similar to the multiple choice style of MCAT, um, and is going to be kind of tricky. So if you're an undergrad pre-med student who hasn't really worked with MCAT style questions yet, it might seem a little bit trickier or like kind of more wordy than what you're used to. But I still think it'll be very good practice for people who are freshmen and sophomores and not really ready to think about the MCAT yet, or just like taking Gen Chem or whatever. Okay. And kind of my goal with this video is to go through this. Hopefully you can try the worksheet before watching, and you can see how I reason through these questions. All right, yeah, let's get started with the first one. So we've got which elements could have a stable isotope with 30 neutrons? Okay, so my mind is immediately kind of being pulled to the word isotope, and I'm remembering that the word isotope means like the same element but with different numbers of neutrons. So my answer choices are going to use iron, nickel, and copper. If we look at iron, for example, iron has an average atomic mass of 55.8, which means that that's the weighted average. So in nature, there can be iron atoms with like 55 protons and neutrons. There can also be some at 56, with 57, or even getting lower, we could do 54, so on. So it's the average of all these different kind of isotopes that exist. But really, we're only going to want to focus on isotopes that are really close to the average because those are going to be the more reasonable answers. So that being said, if the iron has 30 neutrons, that means we're going to add 30 to the atomic number to see what the atomic mass of that isotope would be. So iron has 26 protons. So if it had 30 neutrons, it would have an atomic mass of 56. And you know what? That's really close to what the weighted average is on the periodic table. So this seems like a stable isotope. It seems like a reasonable isotope that could exist. We do nickel next. Nickel has an atomic mass of 58.7 and an atomic number of 28. So 28 plus 30 is 58. And if we did copper, it'd be 29 and 59. So 58 seems pretty reasonable because the atomic mass is 58.7. But copper is kind of looking suspicious because it's 63.5. So an atomic mass of 59 seems kind of low. It seems like, I mean, we're short like 4 neutrons. So it seems a little suspicious compared to the other two answer choices. So ideally, I want to find an answer choice, hopefully, that doesn't include copper. And yeah, that's going to be C. Okay, so I hope that's feeling pretty good. One thing I'll just point out maybe real quick is notice that there's not an answer choice that says 1, 2, and 3. Because as a undergraduate taking the MCAT, you're not really going to know for certainty how to tell what isotopes are stable or not. There's a lot of complicated factors that go into that. And really, what the MCAT likes to do is try and make you think about the best answer. So even though I can't really say for certainty why copper 59 really can't exist, notice the fact that nickel and iron are a much better answer, much more applicable than copper. So a lot of times with the MCAT, it really is all about picking the best, kind of most reasonable answer. Okay, that aside, looking at question number 2, which atomic orbital is highest in energy? Okay, this one's pretty straightforward and kind of just requires remembering the kind of order of the orbitals. So if we did like a basic electron configuration, it'd be like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So, and dot, 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 and keep going. So notice that in general, as the atomic orbitals get higher in energy, they get kind of higher in number, higher in their principal number, and they start moving to the right. So the 1s orbital is the lowest in energy, and the 4p all the way on the right is the highest. So we can rule out the 3s and the 3p right away. No way it's going to be those. And then between the 4d and the 4p, it's important to remember that the d orbitals are kind of like one energy level kind of behind, if that makes sense. So what I kind of mean by that is the 3d10 orbital, or the 3d orbital, is equivalent in energy to the 4s and the 4p orbital, which means the 4d orbital is equivalent in energy to the p and the 5s orbital. Okay, so that means that our 4d orbital is going to be higher in energy than our 4p. Which element has the lowest electron affinity? All right, I'm going to do this one kind of quick because in general with the periodic trends, I think the easiest way to kind of remember them is that all of the periodic trends go up and to the right, except for atomic size or atomic radius. So the size is the opposite, it goes left and down. But since electron affinity goes up as you go to the right, and up, we're looking for an element that is on the left and down. So we're looking for like this kind of region. And potassium was one of our answer choices, and so it's going to be the correct answer. All right, number 4. Which ion is not likely to occur in nature? So the MCAT loves their negatives in questions. So not likely. So we're going to need to rule out the ones that are likely. So this is a bromine anion. Bromine anion. It's an anion because it's negative, and it only has one negative charge, which means it has one extra electron. So it is going to be likely in nature if that added electron is going to bring it closer to a noble gas configuration. Because remember, all the elements would love to have completed electron shells, which is the same thing as saying as having a noble gas configuration. So bromine is right here on the periodic table, and if it gained an electron, it would have a completed shell. It would have the same electron configuration as krypton, so that's great. So this seems very likely. Magnesium 2 plus is going to be the same deal. Magnesium's right here. And as you lose one electron, you become sodium, and then after that, it's neon. So great, we've got a noble gas config. That's perfect. So it's not these two. Lithium is the third element. I'm not going to scroll back up because hopefully we know that it's the third element and it's period, or it's group 1. And the group 1 elements need to lose one electron to become a noble gas configuration. So this one's also good, which leaves silicon as being the correct answer. And if you go and check silicon, silicon dication, so +2, would go from here to 1 to it would become magnesium. And so even though that is moving it, I guess, closer to becoming a noble gas, not actually nearly as good as the other 3 answer choices, which became noble gases with their added or lost electrons. Okay, I'm going to erase everything. All right, so the next question, what do we got? Which element has exactly 5 valence electrons? This one also is pretty straightforward. So in general, as you move from left to right in the groups, you add a valence electron, right? So lithium has 1 valence, beryllium has 2, 3 for boron, and then you go all the way up to kind of 8 over here. And then once you get to the D block, we start adding even more valence electrons. So for example, like chromium is going to have 1, 2, 3, 4, 5, 6. Okay, so that's kind of how this works. And let's check out our answer choices. So Oxygen is group 6, so it has 6 valence electrons. That's wrong. Lead is, I believe it's group 4A. Sorry, oxygen is 6A, I should mention. Lead, I think, is 4A. Yep, it is. Same as carbon. So that has 4 valence. That's wrong. V is vanadium, and it's right here. So this would have 1, 2, 3, 4, 5 electrons, 5 valence. So that's going to be our answer. Oops, do that in blue. Okay, which factors are most significant for determining the length of an atom's atomic radius? Okay, so I can already tell there's a lot of jargon in this one. So um, this just kind of classic test taking, I think, in general, is both the MCAT and professors with regular midterms and finals love to intimidate you with jargon. They really want kind of just, I guess, like almost like fry your brain with lots of jargon terms. And so right away, what I like to do is kind of simplify it as much as I can. So when I think of factors, you know what? That just means things. Which things are most important? I don't know. Important seems easier for me some reason. Which things are most important for determining is useless, whatever. Which things are most important for the length of an atom's atomic radius? Well, the atomic radius is just the size. So which things most important for size of an atom? I'm going to boil that down. So I'm thinking which things are the most important for the size of an atom? The principal quantum number of the highest energy occupied electron orbital. Okay, so the highest energy orbital, that's just referring to, like, if we're doing electron configuration, it's the last thing. It's whatever the last thing is. And the principal quantum number is the number in front of the orbitals. So as the principal quantum number gets bigger, that means the energy levels of the orbitals are getting bigger. And also, it's really important to keep in mind that energy for electron orbitals is very similar to saying size, because if you've got like your random kind of atom right here, you know, our 1s orbital kind of looks like this, our 2s is bigger than that, and then we would have a 3s, which is still bigger. I'm not bothering with the p orbitals, but notice that as the principal quantum number is going up, so is the size of the orbitals. So therefore, yeah, this does make sense. It is going to make the atom bigger. So 1 seems good. 2 says the quantity of protons within the nucleus. So here it's really important to remember kind of the analogy that I said in another video, which is that if an atom was the size of a football field, the nucleus on average would be the size of a quarter. So the protons and the neutrons in the nucleus don't matter for the size basically at all. It's really all about the orbitals that the electrons are in. So this is not right. And then 3 is the number of valence electrons. So this one might seem tempting, but it's not right either, because as we add valence electrons, so here's 2, we could have 4, 5, 6, 7, 8, so on. As we add valence electrons, the atom doesn't actually get any bigger because the orbitals are the same energy still. If they're in the valence electrons, then they're the same shell. So they're the same energy, which means they're the same. So that's not true either. So it's going to be 1 only, or A. All right, 7. Which group of elements contains the element chlorine? So chlorine is in group 7A, right here, and this group is the halogens. This should honestly just be a pretty straightforward fact. Very important. I would say it's really, really good to know the names of these two groups and the two groups on the far left. Okay, so the halogens, chlorine is a halogen. Which atom does not have an electron configuration? So again, another not. does not have an electron configuration of this. Okay, so we can kind of go through these. And I think I have a periodic table down here too. So let's do it. So we've got phosphorus 2 plus. So phosphorus 2 plus would be, it would be here, but it lost 2 electrons. So we're going to go to aluminum. So let's do the electron configuration of aluminum. So this would be 1s2, 2s2, 2p6, 3s2, and then finally this would be 3p1 because we're only in the first group of the p orbitals. So yeah, that's perfect. That's exactly what we were looking for. So this is not the answer because we're looking for the one that doesn't have this. Magnesium 2 plus, let's check that one. So magnesium is right here. And if it's 2 plus, well, it's actually going to move to the left. So it's going to have the same electron configuration as neon, which ends at 2p6. So this one's definitely wrong. All right, so this would be our answer. This one does not have the same electron config. Okay. Which of the following explanations for why period 3 elements can form more than 4 bonds is true? So just as a quick review, this is basically saying that the period 3, so basically row 3 elements, can form more than 4 bonds, which kind of breaks a rule that you learn about the period 2 elements. So the period 2 elements follow what's called the octet rule. Which means that they can really only have up to 8 electrons in their valence shell before having no more, which each bond, as we'll kind of see more in another video, each bond counts for 2 electrons. So yeah, that means they can only have 4 bonds in period 2. But period 3 breaks that trend. And the answer choices, to be honest, they're kind of full of jargon, and I don't want to rule out each one because this one is really kind of just important to just know it. And the true answer is C. So they have an empty set of d orbitals that can accept additional bonding electrons. And that's true. So we talked about this a bit in either video 3 or 4, but basically what happens is um, even though this kind of area of the periodic table is empty, remember when we do electron configurations, we use the 3d orbitals too. So the 3d orbitals would kind of be right here. They would be in the third row, the third period. But the thing is, they're higher in energy, as we saw. Remember, the 3d orbital is the same energy, more or less, as 4s and 4p. So these elements, which have 3p orbitals, don't bother to fill their 3d orbital. But they actually do have 3d orbitals. They're just empty. So that's why they can kind of fill them and get even more electrons sometimes. All right, 10. Which bond shown is the most polar? This comes down to electronegativity. So I wrote the electronegativities of hydrogen and carbon here, so 2.2 and 2.5. And the bigger the difference in the electronegativity of two bonded atoms, the more polar its bond is. So 2.5 minus 2.2 is a difference of about 0.3, which is really small. That's considered nonpolar. So this would be considered a nonpolar bond. And if you look at B, it's the same deal because they're the same atoms, a carbon bonded to a carbon, so their difference is just 0. It's completely nonpolar. C is carbon and a chlorine, and D is carbon and a nitrogen. So this is really going to come down to which element is more electronegative, carbon or chlorine or nitrogen. And it turns out, if you're kind of following your periodic trends, electronegativity is up and to the right. Fluorine's the most. Fluorine is number 1 most electronegative. And I kind of like to remember this as like oxygen and chlorine are number 2. They kind of are tied for number 2 in electronegativity. You don't really need to know the exact values, I would say, but it's good to remember that oxygen and chlorine are tied for number 2. And then kind of in third place is nitrogen, and fourth place is bromine. Yeah, so bromine kind of gets fourth. So if we're comparing chlorine and nitrogen, well, chlorine's the second most electronegative element with oxygen, so it's going to beat nitrogen. So that'll make its bond the most polar. So C. All right, the next question is, which atom does not have the same electron configuration as krypton? Okay, so we would need to do the electron configurations for all of these and see which one's not right. So if we look at ZR 4 plus, ZR is right here, and it has 4 plus, it's lost 1, 2, 3, 4 electrons. So that one's good. We can rule that one out. Bromine is right here, and it's gained an electron, so it's also got the same electron configuration. Selenium 2 plus. Okay, so selenium's right here, and if it was 2 minus, this would also be perfect, but it's 2 plus, so it kind of went the wrong direction. So this one's not the same, and it's the correct answer. Well, which atom has the largest effective nuclear charge? Okay, the way you calculate this is it's basically Z effective, which is effective nuclear charge, equals the number of protons minus the number of inner shell electrons. So for A, this atom has 4 protons, it has 2 electrons. So this is actually a cation, right? So it's a 2 plus cation because it has more protons than electrons. And if it has 4 protons, that means it's beryllium. And so the number of protons would be 4, and it actually doesn't have any inner shell electrons. It has 0 because it only has 1 shell, so that would be considered the valence shell. So its effective nuclear charge would be 4. Okay. B, if you look at B, it's got 2, 4, 6, 8, 10, 11 protons. 11 minus, so all of these would be the inner shell. So this is going to be 10 inner shell electrons, and it has 1 valence on the outside, all the way up here. So this is going to be 1. Here we've got 3 minus 3, or sorry, oh my gosh, 3 minus 2, because it's the 2 inner shell, equals 1 again. So far, A is definitely our answer. And then finally, D is 2 minus 0 again. And this one just equals 2. So the answer is going to be A. 13. Which of the following statements explains which of the following statements explaining why effective nuclear charge decreases going down a group is true? Okay, this is another kind of jargony one, but really, yeah, it's just saying, why does effective nuclear charge decrease going down a group? So this one, I might honestly be tempted to just try and think about it before I read the answer choices a little bit, because I know that basically as you go down the group, right, you're adding a lot more electrons. So like lithium has 3, and it has 2 shells. So this could be like lithium. And then if you look at sodium, it's going to have a whole nother shell. And then potassium would have an even bigger shell, and it just keeps getting bigger and bigger. And effective nuclear charge, right, is the proton pulling. So as electrons get further away as you go down a group, they get pulled a little bit less because they're just further. They feel less of that attractive force of the protons. So one of the things about effective nuclear charge is that the calculated number is the same down a group, but you need to remember they get further away. So the answer should be something like that. So A, the atomic number increases down the group, which increases the force of attraction since there are more protons in the nucleus. This is kind of the opposite of what we want because it's talking about increasing the effective nuclear charge. B is the orbitals of the electrons are increasing in energy, which means they are further away from the nucleus. That seems pretty good. This seems plausible. C, the orbitals of the electrons are decreasing in energy, which means they are further away from the nucleus. That's not true. As the orbitals get further away, they also increase in energy. D, the quantity of valence electrons is increasing, which increases the electron-electron repulsion effects. This kind of seems tempting in some ways because it seems like a true statement, maybe, but it doesn't really have anything to do with effective nuclear charge because, as you remember, our formula only looks at the inner shell, not the valence. So D is wrong, and B is what we wanted. It kind of incorporates distance, which is the important thing. 14, which of the following statements about ionic bonding is true? They occur with two elements with similar electronegativities. This is the opposite. That would be for covalent bonding, maybe even for nonpolar covalent. B, they occur frequently with group 4A and 6A elements. So group 4 and 6, so that would be this group and this group. They obviously can bond with each other, but the electronegativity difference between carbon and oxygen, or like silicon and sulfur, or sulfur and carbon even, isn't that big. Even though oxygen is the second most electronegative element, carbon is pretty electronegative compared to a lot of the other elements, especially the elements kind of in this region of the periodic table, and even a lot of the metals. Those tend to be really low in electronegativity. So groups 4A and 6A, they don't form ionic bonds. D, they form very strong bonds held together by the forces of attraction between a cation and an anion. That's true. That's definitely the case. You really need that strong kind of force of attraction from a negatively charged thing and a positively charged thing to have an ionic bond. And then D, they only occur when one atom permanently receives one electron from the other. So this is kind of classic, I feel like, deceptive question or like answer choice tactics where it says something that seems totally correct. It's like, yeah, that is ionic bonding. It's when one electron permanently gets an electron from the other. But the thing is, whenever you see a word like only, you immediately should kind of have like a little red flag raised up in your head. Like, in general, really strong words like only or all or like always, every, like those kinds of words should be kind of like a little bit of a red flag because it's very specific, right? It's really hard for something to be always true. And so if they only occur when one atom permanently receives one electron, it's really this one electron that's going to be wrong. So ionic bonds can occur where two or more electrons are given away. It doesn't have to just be one electron. 15. How many electrons can exist in a 2p orbital? Um, this one may be a little tricky and is really getting at the difference between a shell and an orbital. So remember that really when we say 2p orbital, we're actually talking about three 2p orbitals, right? There's the 2px, 2py, and 2pz. So the word orbital, you always can only have two electrons in an orbital, and they exist in, there's two per these three orbitals. So that's why when we do electron configurations, we have 2p6. The 6 is coming from the fact that really you have three p orbitals, but we're just kind of lazy and just say p and kind of chunk them together. But the answer is 2. That's kind of to explain for anybody who might have picked B. 16. Which of the following is the best explanation for why there is a limit to the number of electrons in an orbital? Okay, so We've got the Pauli exclusion principle forbids electrons from having identical quantum numbers and spins. I'm going to go ahead and say that that is actually the correct answer, but I want to break down why the other ones um, aren't true. So A is correct, and even though it's very jargony, that really is how you explain the Pauli exclusion principle. But let's look at the others. So B, the electron-electron repulsion interactions become too great. Well, that's not really the limit, or that's not really the reason why there's only two electrons in an orbital. It really has to do with the fact that every electron has a unique quantum number. So for example, there's only two electrons in the 2pz orbital, and then one of those electrons has the up spin, and one of them has the down spin. And that's true for every orbital. So you can't find an electron that has the same exact quantum numbers. And again, quantum numbers refer to the 2, the p, the z, and then the up or the down. So those are the four kind of quantum number qualities. So B is wrong. C, the electrons eventually become excited and enter a higher energy orbital. That's just kind of BS. It's not, yep, that's not true. The principal decay modes of orbitals is directly proportional with the number of electrons. That's also BS. Don't even really know what that is or even if that's real. Okay, 17. What type of bonds are found in a molecule of water? Okay, so this one is directly out of the last video, and we talked about how since it's oxygen binded to hydrogen, their electronegativity differences are pretty big, but not huge. So it ends up being a polar covalent bond, and that's what makes water really special. Hydrogen bonds might have been tempting to some, but remember, I guess we haven't talked about this in the videos yet, but what we're going to learn is a hydrogen bond specifically refers to an intermolecular force. So it only refers to multiple molecules. So it doesn't actually refer to the bond between atoms. So like oxygen, hydrogen here, they have an intramolecular bond. It's a bond between atoms. Intermolecular forces are bonds between multiple molecules. So you need two waters, one, and then you can have hydrogen bonds in between this. So we'll see this more in like kind of the next few videos. 18, what characteristic is most applicable to noble gases? This one is pretty simple, I think. It's A, they're inert, which means that they are unreactive. They don't react with other elements, and that's because they have full electron shells. 19, the statement the number of valence electron increases ... is correct for, okay, so we need to fill in the blank. So the number of valence electrons increases as electronegativity increases. That's not going to be true because electronegativity increases as you go across a row, and that's true. Yeah, the valence electrons do increase as you go across the row, but they also increase going up a column. And remember that all the elements in a column have the same number of valence electrons. So that's not true. B, as the atomic radius decreases, that's also not going to be true for the same reasons as A. C, across a period. Yep, that's going to be the answer. So as you go across a period, every element, you're getting an extra electron in the valence shell. Okay, I hope that went well for everyone. I hope these explanations kind of made sense and that this worksheet, I'm sure it was kind of tricky. I did want it to be a little bit tricky, right? Because the MCAT is tricky. I hope it was making sense. And you felt well prepared from the previous videos. Anyway, thanks for watching, and I'll see you on the next video.